Welcome to XOR Episode 6, with our guest, Joseph Martin, the robotics engineer.
My degree is just mechanical engineering, a master's of mechanical engineering.
It's surprising how much robotics you did with mechanical engineering. Mechanical engineering in the UK can get very different.
Oh, yeah.
It can even be like oil and gas.
Oh, yeah, that's the same.
Yeah, you have a very modern
So there's like
mechanical engineering.
At Virginia Tech, at least, and I imagine at other places it's similar. There's like tiers. So you have like the top level, like the name of your degree is Master's Mechanical Engineering, and then below that at the school, you had like robotics and control. So I would honestly say it's probably more like mechanical engineering, control theory, robotics, in terms of like going down to like the specifications.
But are they official somewhere, like on your degree certificate?
No, I don't think anything on my degree specifies anything about robotics, just my work experience. Because yeah, like mechanical engineering can cover everything from, controls to thermodynamics to materials science to fluid dynamics. I'm saying all of the things that were in the lab class that I was a graduate teaching assistant for. That's where I'm getting that list primarily. So yeah, that's the same. It's a super broad category. But it is, and like even robotics, like you can get into like way different, like working on robots. There's so many different like points that you can come into that.
I agree.
from.
And that's what I like about robotics. I mean, you can be doing linguistics.
Right.
And still be considered a robotics engineer.
Right.
And it really caters to people who are who love doing a lot of things, because there's so many things to do.
Right. Yeah. No, that's definitely like a big thing of why I like it, because like there's so many different levels and elements and integrations of like different things. So you get to like talk to all the people. Like it's not just everyone out in their own separate corner. It's like, hey, I've made this advancement. Now someone that I'm never going to speak to is going to use it at some point somewhere down the line. But like when you're working with hardware like that, like even if you're primarily like working on software, you got to talk to the hardware guys, because that's just the physicality of it is just a fundamental part of it. I know like with a lot of robotics research, there's some things where a lot of it gets stuck because the people involved, for whatever reason, just can't get involved with like the hardware, right? So like it stays in software land, and you can get a lot of stuff to work in really cool ways in software, but actually getting it to work with like physical extant things is like just a whole different ball game. But it's also, to me, it's like the fun part of the ball game, because it's like, yes, this is like a real thing that works in the real world.
I wanted to ask basically the difference between a degree in the US. Do you think you got a lot of practice? Because I think that, for example, for my degree, the practice made me the better, like make me stood out. And American universities tend to have a much higher budget. So when I see universities in the US, I don't know, like there's Penn State and there's Penn State University, right? Or like Caltech, MIT. You got like those guys have like an unlimited supply of humanoid robots that are like $500,000 each, government contracts. Like you guys have a lot more to play with. Did you get that feeling that you got to?
I definitely benefited from the opportunities that I had to play with hardware. Absolutely. And that was the part of it, though, was like, I think part of it too, though, is like you do have to like seek that sort of stuff out. It's not something that just sort of falls into your lap. Even if you go to like one of the places that's like known for it, right? Like you gotta, because even when there's a ton of hardware, there's also a ton of projects that don't involve that hardware. There were like I did not have to take that experimental robotics course that had the wheeled robot that we worked with. Right, that was not required. It was, I think it maybe fulfilled some requirement, but it wasn't a specific one. But I did it because it's like I would like to work with a real physical thing, and it was completely different than it was, instead of legs, it was wheels, and that was completely different from my perspective, at least. I didn't want to do flying. Flying stuff is really cool. But the way that I get nervous about things, I would not be able to like have the guts to like do something and be like, now it goes in the sky.
Oh, the drones.
Yeah, drones and just controlling stuff like that. Like with a wheeled robot, like I guess the worst thing it can do is it can speed off, which isn't great. But like that, like a lot of things have to go wrong. Maybe not a lot, but like that's an active going wrong, right? And with a legged robot, the sort of passive going right, wheeled robot passive going wrong is it just stops. Legged robot passive going wrong is it falls over, which is not good for the robot. And if it's not good for you if you're close to it, but other than that, not usually a big deal. The a flying robot, the worst thing that happens is it falls out of the sky, which to me just feels worse. So I think it's cool, and I'm not saying I'd never get involved with it, but I was definitely like when I was looking for opportunities, I was looking for things that were on the ground. But like, so you have to look for those sorts of projects, but even involved in that, like there's, especially in controls, you can just do math. Controls, if you want it to be, can just be math.
Yeah,
There's a lot of math. A lot of my research was math, like theory and like, loops, periodic cycles, and like how to get things to follow a periodic cycle, because like that's sort of like how gate patterns were working in that formulation. And you can stay there and you can do a lot of cool stuff in that area, and there'll be tons of projects for that to happen, and a lot of those too, probably because the main thing you just need is a fancy enough computer to do the simulations that you need. You could arguably do control theory without any simulation. You could just do the math. I think people like to see the simulations because it kind of like is a quick way to see that, yes, that math works without having to actually like go through all of the math and understand it. It's sort of like, I would bet that it's like you look at the simulation to see whether or not it's worth looking through all of the math. Exactly. Right? Because if there's not a simulation, you could end up going through all the math to find out, oh, this doesn't work. But if there's a simulation, you're like, well, it at least looks like that increases the chances that this math will work out eventually. So now it's worth me going in and understanding what's going on in there.
It's visual intuition that it provides. So you worked mainly, you would say, like your specialty in control theory, right? Is there a specific reason you chose that? Or was it just chance and you were like, yeah, why not?
It was a little bit. So like when it came time for that, what I had done, I had just finished, or I was, wrapping up my physics undergrad degree, which is not control specific in any way. There was no hardware that I was working on really there. And I had sort of gotten to the point where it's like, okay, I've done this. I was really interested in it, and I also felt like I had gotten what I wanted to get out of it. And so it was sort of like, okay, if I could, I'm just going to decide what I'm going to do next. What would be the coolest thing that I could do with my background? What's the coolest thing I can pivot into now? And I was like, it would be very cool to work on robots. And so I was like, okay, well then where in the sort of stack of working on robots does my education best fit in? And with control theory, it's sort of like taking that transition of the math of the physics that I had been studying and then applying it into real world scenarios. And so like I could take the math background, get a start there, and then take some of the computer science work I had been also doing in undergrad. I was like, okay, I can do the math, I can do the computer science. So what I'm missing is a bit of what some control people who had done mechanical engineering undergrad, some of the control theory that they would have picked up. So I would have to catch up on that. But the way I was framing it, 2 out of 3, that seems like the best insertion point for me. It's where I have to catch up on the least. I still had a lot of catching up to do in a lot of different areas, even though like I think at least at Virginia Tech, I think you only took like 1 or 2 control theory focused courses. Plenty of the mechanical engineers that I taught the control lab to had taken 0 control courses. And it was like, okay, well, I'm just going to teach you all of this control theory that I like just learned to teach this lab course.
Yeah.
The blind leading the blind is a phrase that people would maybe apply to that situation.
I had very little control theory experience and very little math experience. I joined robotics from, I guess, the software and electrical engineering. Um, tell me more about basically the work that you did on the control side for the legged robot itself. Like, what was your not thesis about? Like, because it will get like very technical very quickly. But what was the inspiration behind your project?
So like the general like inspiration of the lab was like basically a lot of ways that legged robots are controlled now are with the formulation called MPC. That's like the bread and butter of the legged locomotion industry right now, to my understanding. And
That's model predictive control.
model
right?
predictive control. And like one of the key things that does is it basically takes the robot is in a state, and it basically models what the robot would do if you applied certain control to it. And it does that a bunch of times. It predicts the future of like, okay, and then it says, okay, based on what I want to do, I'm going to optimize the control to get that future. But simulating that whole robot going into the future, like especially with a 4-legged robot, right? That's 12 motors, and then you have 6 degrees of freedom that represent the position and orientation of the robot. That's 18 degrees of freedom. That's a really complicated workspace. So a lot of the time what happens is, okay, let's reduce this problem into like basically we've got a ball and we can apply a force to that ball. What force do we need to apply to that ball to get it to go in the direction that we want? And that ball kind of represents the center of mass of the robot. And so you take that problem down, you shrink it. You can shrink it to different scopes of degrees of freedom, but it simplifies the math. It simplifies the computation. The research that I was doing was like, is there a computationally feasible approach to controlling all of the degrees of freedom actively? And so that was sort of like, that's the hybrid zero dynamics full degree of freedom control was sort of the idea of it. So so what you do is you would design a periodic gait cycle, right? So like basically if you're walking, right, you're basically taking a step, and then you repeat, right? If you're just walking forward. So all of the positions of all of the motors and the body and everything repeats. And especially with 2-leg, you can also like take one step and then mirror it and then do it again. So you're really only taking one step and doing it over and over again and just flipping it each time, right? So it's like using like a full order control algorithm to drive the robot to the periodic gait cycle that you design, so that if any of the degrees of freedom end up off of their cycle, what's the best thing to do to get them back onto the cycle? And so you optimize that, and you get some emergent behavior. Like I was working on a robot that was bounding, and so one of the things is like when the robot's in the air, it can do very little to control itself.
Bounding as in the way it hops, right?
Yeah, so like
that's the
2 legs on imagine 2 back legs on the ground, you're in the air, 2 front legs on the ground,
like
you're in the air.
prancing, right? That's what it's called.
Bounding is just there's like apparently technical words for all the different types of ways you can put 4 feet on the ground and move forward. Bounding was that. Double stance of the back 2 legs, flight phase where no legs are on the ground. Double stance of the front 2 legs on the ground, flight phase where no legs are on the ground. Repeat. And like one of the sort of emergent behaviors of the optimization was like seeing that, okay, well, we can't control the orientation of the robot that much while it's in the air because you're not able to push on anything. And legged robots in general are designed such that their legs have very little influence on the trajectory of the body, because for those theories that use the simplification, they work better if you can't ignore the fact that the legs exist. So if the legs dynamics don't matter, then you can simplify them out of your math. So that's why, like with proprietary robots, the legs are very light. There's other reasons for that too. You want your legged robot to be as light as possible because then it consumes less power and all that. But like one of the emergent behaviors that saw through that optimization was like how the robot would like position as its body like orientation left the periodic cycle, it would adjust its feet forward or backward. And so when it landed, it would drive the base. So like if it was, tilting too far forward, it would push its feet out forward and land with its feet farther forward than usual. So that would drive the base back, and the other way around.
So your goal was to basically try to compute the whole spectrum of degrees of freedom quicker?
Just not even quicker, just like address all the degrees of freedom in a computationally feasible way. Like there's no way, like we do a lot of work offline, and then that way we can still control. We're not modeling out any of the degrees of freedom. And the way that we make it so the robot can still do things online, right? With MPC, you could, like, there's nothing in the algorithm that prevents you from plugging 18 degrees of freedom into an MPC algorithm, but the robot isn't going to be able to simulate that and optimize across it in time for it to make a decision at the next control time step. So it's like a formulation to offload. How much of that gate planning can we offload to offline work? And then that way we can optimize with all the degrees of freedom offline so that we're not having to make the simplifications. And if you can do that, then you can expand that to different techniques. You can, there's research showing that like you could basically design a planar gate, and then you could, there were ways that you can incorporate.
What's planar gate?
Planar, basically, you're controlling the robot as if it's in a 2D plane.
Right, forward and backwards.
Yeah,
right.
so like forward and backward.
Right.
And then you could integrate a separate controller sort of layered on top of it that would adjust that gate based. This isn't what I worked on, but you could change like the angle based on like integrating a different controller into it. And like the idea was like to try to move towards a system where we can control the robots without having to simplify things out of it.
Would you get, what type of better performance would you get? I mean, you're sacrificing some speed in doing a lot of computations. Let's say you've done all the computation on all the degrees of freedom. How would you get better performance? Like, do you step in a better position?
I mean, it basically opens, like, that's the thing about academic research too, is that like you're starting at like the ground floor level. Like even in commercial space, right? Robots are having trouble finding places where they're useful. Like not where they're useful, but where they're more useful than what people are already doing. And so I would say also in research a bit too, you have a little bit of that too. I'm not saying that it's entirely a solution looking for a problem, but the sort of higher level long-term goal, right? Part of my research was being part of sort of the foundational body of work to say this is a viable option for integrating more complex controllers. The goal is then to say now we can like overtly control more complex maneuvers rather than like where certain model assumptions wouldn't necessarily hold, if that makes sense, right? So like when you simplify the robot, you have to make assumptions about how that robot is designed, what that robot is going to be doing. The idea with this formulation is that through the process of addressing things offline, going through an optimization process offline that could be generalized, you could apply it to anything without any sort of online tuning. And you could apply it to robots with ideally arbitrary degrees of freedom, arbitrary constructions, like, orientations. Doesn't just have to be like a humanoid or a dog-like robot. But it was like really like groundwork level stuff too. So like some of the like specific application work wasn't quite in the scope of the research. It was sort of like, my understanding too was that like part of the goal was to sort of establish itself as like a co-equal strategy to MPC, which to my understanding is currently dominating like at least the commercial industry, because it's very powerful and there's been a lot of research done into it. And it's very good. Like I also like MPC. So
This is the XOR.
Let's say if there is a software, electronics, mechanical engineering, there is like also within software, you know, not just only doing the math, but you have to like somehow write this math in very efficiently. You have to know in depth how computers work, maybe leverage, you know, programming languages. Which one did you struggle with the most?
Yeah, I mean, definitely the hardest part, I don't think this is unique to me. The hardest part is taking the simulation over to the robot itself and like getting everything to work. Like specifically the transition between software and like simulation and hardware, software and hardware. And like part of it too was like the lab was really small, so we didn't have people who were like dedicated to that. I think it started expanding a bit after I graduated. Like they were in the process of building it up. I mean, when I first joined the lab, it was like me, one other long-term person, and one person who was there for a short term. Like that, it was like kind of like an exchange sort of situation. And so like as we went on, we built up the team with more people doing different things. And so like, right, you need people who understand like every single level of it. And starting out, we didn't have people who understood like every single level, or at least were confident enough that we knew that we would not break one of the 3 robots that we had. So that was tricky. I would also say like, honestly, like I struggled a lot writing those papers. It was way out of my comfort zone in a way that I did not realize going into, because I've written like, and I was, you know, good enough at writing in my liberal arts education. I studied physics, but I was at a liberal arts school because I also wanted to. I wasn't like, when I first started doing physics, I wasn't like 100% dead set on doing physics in undergrad. It was just like where I was starting. I thought I would be good at it, but I also wanted to keep my options open. And I liked the other stuff that I learned. I liked having like sort of that breadth. I didn't do, so I did writing. I did some academic writing, but nothing like writing writing a paper, man, is scary. You got to send it off to a bunch of smart people who are way smarter than you, way objectively smarter than you. And then they're going to look at it and be like, this is a good science or this is a bad science.
Yeah.
And
I've had it where, I mean, first time receiving a peer review from like a professor, and then you look them up and you're like, oh my God, this guy's a monster. Like he's been in the industry for like 20, 30 years. He's looking at my paper that I wrote as a university student. It's probably like, I don't know, so primitive to him, and has 1,000 mistakes that he has to look for. And you're like, oh my God, forget that I exist. Please don't crucify me.
Yeah. So
do you think it made you, I have this hypothesis. There, we had, for example, a computer vision course, and it had a very, at the end of you had to write, it was all coursework based, and you had to write basically a 3-page paper. And there was it was a huge course. It was like a 3-4 month course. And you had to write a very, very short, like you have to include the entire semester worth of work in a very small review. So I wrote it once, and it was 10 pages long. And then that was never going to work, right? So the limit is like maybe a couple of thousand words. And then I gave it another review, and then I realized actually half of the stuff that I'm talking about is garbage. Removed it. I was on like 5 pages, and I was like, actually, half of these plots actually show the same thing. Let me combine them. So like that limit that they put on me, that limit, like for example, the IEEE puts on you of I think 6 pages.
Yeah.
It just enforces you So then you like condense information, and then you review your work. That magnifies my understanding of it, because the amount of times I've read through it, compressed it, just left only like diluted, what's the word? Purified, distilled. That's what they're called, like distilled papers, right? Like you distill information into very small volumes, helps your understanding. I think a lot of people complain about writing papers, but I think it's actually very beneficial that you have to do them, and they're so difficult, and there's a lot of seemingly artificial constraints on the amount of words and the amount of plots that you can do and the titles that you can put. What do you think?
I think it's absolutely like useful. Like I did not like doing it, but that is not exclusive to it is a good thing for people to do. Right? Like it was the frustrating part of it to me was just more that I wish that my education had better prepared me for writing like that, because I don't know, in academia, all throughout school, really, it feels like whenever you're given a writing assignment, you have like a page minimum, right? And you're expected to write as much as you can fit on the page. And it's like you're getting up to a certain word count. And so that encourages you to do tactics where it's like, oh, I'm going to blow up this one thought into 3 paragraphs because I have a minimum that I'm trying to target. And then suddenly that immediately gets flipped. And now you have a page maximum. And you've got what's being valued now is like really specific, intricate, right? Not just like you have to deal with both condensing your ideas, but also making sure that you don't leave confusing ambiguity. And like, for me, my gut reaction, even in like speaking and writing and everything, is to like add disclaimer upon disclaimer, explanation upon explanation. And like, it's a good thing to like be in a situation like, no, you get one sentence to communicate this idea, and you also have to not have any ambiguity in that one sentence. But then sometimes there are going to be points where it's like, you have to come to terms with the fact that there's going to be some ambiguity in this statement, but it doesn't matter, right? There are certain things where it's like, you really want to specify this, but it's not important to the idea that you're trying to communicate.
I really agree with you. I don't think I've thought of that before. It's like how in the beginning you're asked to, maybe in high school, you're asked to like romanticize your writing and just blow it out of proportion, and then creative writing. Whereas then you're like, oh, this is technical writing now. So you are actually asked to, be terse. Is that the right word?
But even in like academic, before like for homework, right? For your classes, when you're asked to write, you're asked to write at least this much. And that's not directly saying be romantic and flowery and long-winded, but like that's the kind of thing that will, if you have to do that for 5 different classes, that's the fastest way to get a bulk of writing done. And to me, so you go through, you're like, okay, here are the 5 things. I'm going to put the 5 things in, and now I'm going to write a bunch of stuff about it to get to the word count. But it's not about communicating. A lot of the time, it's not about communicating the ideas. I mean, it is about communicating the ideas, but then there's this extra bit of you have to show that you put effort in. And it's easier to show that you put effort in if it's 5 pages, especially if the person grading your assignment is, a graduate student on a stipend who's just trying to get by and has to grade like 40 of these in a week. And so like I think that, and this is my personal experience, I can't speak to other undergraduate experiences or anything like that, but like even just for the regular coursework, I feel like having that structure of like, you need to communicate all the same ideas, and you have a limit, and you should use the limit, right? You shouldn't write less than the limit, because if you're writing less than the limit, then that means that the ideas that you're talking about probably are not worth. There's not, or not, maybe not worth, but you need more. If you're not reaching the limit, then your idea doesn't have enough substance. It needs more substance to be sort of put all together. Maybe. I mean, it's not an easy problem. Like, I wouldn't just be able to, like, I'm a teacher now and I'm going to fix this problem that I've found. But that is, I felt unprepared for it when I encountered it outside of my studies.
That's interesting that you say that. You chose the writing part as like, I would have expected an answer, something like, oh, well, I wasn't as good at C++ as I needed to be. You're like, actually conveying information. It was like a challenge. Not that you maybe misinterpreted that it was a difficult part of the writing, like you weren't prepared for it, right? I actually have a theory about this, that overall in the tech world we struggle, or tech world academia, we struggle to convey a lot of information. It's like we have much more opportunity to do so, right? Through like social media and like all these like websites. I mean, but the, let's say, distribution of knowledge is actually suffering at the moment. Like I feel like that. Like, do you feel like there is some niche that we're missing in education about how to present your work?
Is it a niche that we're missing, or is it also the kinds of people who end, like, on a grand scale, who end up in this field, right? Their best skills are not the skills that help in ways that other industries, right? Like, if you're studying like political science, I would imagine that like you're also the kind of person who like is good at and enjoys like that kind of thing. Whereas like I don't want to be like every single engineer is a shut-in that doesn't like to talk to people. But like I would say you can get by in an engineering being a shut-in and not talking to people in a way that you can't in a lot of other fields. You can get like, I mean, when I was grading these papers, when I was a teaching assistant, I mean, I don't think a lot of these kids had written like a paper in years, and they were like, suddenly they were getting like B's and C's. And like, I didn't think I was a very harsh grader. I mean, they probably would disagree with me, but it was like, there's literally like a to-do list that they just wouldn't follow. And the only way I could explain it is just a lack of experience. And you can get all the way to the end of your math and science-based career, understanding how to do math problems, understanding how to do coding problems, but not having communication skills.
I think that's exactly, you hit it on the nail. I think you've set the question up even better than I did. It's like let's say you are graded on a very different set of skills than that is actually far away from communication.
Right. Yeah. I'm sort of formulating this take as I'm explaining it. So if I sound inconsistent, that's
no, it's really good.
But like it's not that engineers are bad at communication, but it's that if you are bad at communication, you can still be an engineer. And
that's probably the best field to succeed in.
And so that,
right?
Then you get to, and like, and that was part of it too. Cause like, I don't know. I have been told, and I'm trying not to stroke my own ego too much. I've been told that when it comes to explaining like the ideas behind what I am working on, people who have no experience in the field feel like they have a better grasp of what I'm talking about. And I feel like that was part of the struggle when writing for like scientific academia, writing a research paper, writing a master's thesis, is that I'm not talking to people who don't have any idea what I'm doing. I'm talking to people who probably know more about what I'm doing than I do.
Right.
And that like direction of communication where it's like, there's so many things that like I'm putting like why am I explaining this basic Lagrangian equation of robotics that every single person in this industry knows? Every single person is like the fundamental equation, but I still have to put it in the paper, even though everybody knows it.
Right.
And it's like, and I have to put in all of these things that everybody, like the first half of the paper is stuff, half is maybe an exaggeration. It's what it felt like. It's stuff that everybody who's reading this paper knows about for the most part, because I'm writing it for them. But then there's like this social expectation of like, this is how a research paper is done. And I'm sure like when it comes to, it helps people who don't know the field too. But like, it's weird, like the differences in audiences. And for me personally, I like taking the complex ideas down, breaking it down into the ways that can be understood by someone who has no idea about the field. Because then also like that's how I also like taking in information from other people, like people who can break it down into a way that like, even if I don't actually understand it very well, after they have told me about it, I feel like I understand it. And it gives you the seed to start looking and understanding more things. And that I have found I enjoy that kind of communication about like just science and, you know, even just like taking on like, you know, with it's physics in particular, there's lots of like social, I don't want to say misconceptions because it's not even like that. It's just like someone, you know, Einstein had a theory of relativity and people are like, so morality is relative. Einstein discovered that morality is relative. It's like, that's not even a little bit like, that's not what the relativity means. It's just,
right.
it's just the same word, but like it means something completely. It just, in fact, yes, we knew about reference frames. Like you could look at something and say, oh, if I'm standing on the train, it looks like you're moving really fast past my window. That's not an argument for moral relativism. That's just how things work.
You're basically saying that a lot of, you know, like issues in science also came from miscommunication and like the lack of ability to just like condense and encode and decode information. And
like, I don't think this is just like engineering and science, but I think in general, like they're to me, I will sometimes see things like described or like codified into like the way we talk about certain scientific things. And it's like, okay, I as soon as I see this, like, I understand exactly how this is going to be misinterpreted by people who don't know, who aren't familiar with this topic from the ground up. And it's going to cause a lot of confusion for something that isn't actually that confusing. When there's plenty of stuff too that is very confusing about. I come back to physics because physics has a lot of stuff where it's like quantum stuff is like, what's even going on there? But then there's other stuff that's like, no, we figured this out. It's weird, but we figured it out. But like, I don't know. Do you know about Schrodinger's cat? This is my mountain. This is my molehill that I've been making into a mountain for myself recently.
Well, yeah, I have a Hollywood interpretation of what Schrodinger's cat
right?
is.
So it's for those in the audience who do not know about Schrodinger's cat. There's the quantum uncertainty principle, which like very high level says that a quantum object, a particle, imagine like a little dot, exists as both a particle and a wave, and it has properties that exist in a probabilistic state that only gets determined when you measure it. All right, so the wave function collapses, and there's some it assumes a state when you measure it, but before it is in a probabilistic superposition of states, which is a weird thing to say. But
what defines superposition?
It just means that like it is simultaneously existing in all of these states, and when you interact with it, it will end up in one of those states. That's the very high level description of it. And so the idea behind Schrodinger's cat is you put a cat in a box, and you put a vial of poison in that box, and you put a little tiny hammer attached to a Geiger counter in the box as well.
A Geiger counter is what measures radiation.
Yeah, measuring radiation, which is like a quantum phenomenon. Like the emission of radioactive particles is something that is determined by quantum physics, and it's random, not in the sense that it's an equal probability of all likelihood. It's sort of like you could have a random number generator where like 90% of the time the number is 13, but it's still random if you can never predict when it's going to be 13. So it's sort of like that. It's not like 50-50 across the board. It's not every single superposition state is as equally likely as the others. It's just that you cannot predict it based on a deterministic set of factors. So the idea is that you do not know from quantum theory when the Geiger counter is going to go off. So that means that the Geiger counter is also in a superposition of states. And so the hammer is both in a state of being hit and not hit at any given time. The poison is in a state of being released or not released at any given point in time. So the cat is in a superposition of states of being both alive and dead, is the idea. And
unless you measure it, unless you take the box.
Yeah, unless you open the box and you observe it. This is to me. There's apparently more arguing about this in the scientific community than was under my impression. To me, it's like it just seems like it's when you measure it. It's not it's what people will use it for is like this. Oh, this is the scientific proof of consciousness because you need a conscious observer to collapse the state. To me, it's like no, you just need to measure something. Like the idea of the illustration was to like say. It's weird that when things are very small, we treat them like quantum probabilistic superpositions, but then that leads to deterministic outcomes, like a cat being alive or dead. And so it's like at some point, there has to be a transition between those two realities, the reality of the very small and the reality of the very big. But the measurement still happens. It's the issue with measurement. Again, this is my perspective, and it seems like maybe people much smarter than me are still arguing about it. So I may be completely wrong. But like to me, it's like to measure something, you have to interact with it. You cannot measure something without interacting with it in any way, right? To see, like, to look at you hold a ruler up to something, you have to, like, the photons have to bounce off of that ruler for you to see what it's measuring. So it's sort of like that, where it's like, you can't, like, if you're trying to figure out what something is doing, you have to, like, shoot something at it and then see what that thing does. Right? It can't just exist. It has to be interacted with in some way. And by interacting with it, you take the probabilistic states and you collapse them into a determined state. And so that's just happening in the Geiger counter. Is the short version.
The issue
to me.
Do you basically you brought that up because you think that Schrodinger's cat is like a good or a bad example of basically science communication?
I think it's a bad example of science communication because it's just like this. It's when quantum theory was first being like investigated, it was like part of an exchange between a couple of scientists, and it was a guy that was basically saying like, "Hey, this is like, here's what you're proposing. It's kind of ridiculous. You're telling me that based on what you're saying, this cat is both alive and dead. That's ridiculous. That can't possibly be how things work." And it was sort of like, okay. And to me, like the people, it seems like the response was, well, that's not how it works. And I think even the people making the thought experiment were like not thinking, oh, so this, if quantum was real, this is how it would work. It was sort of like just sort of trying to illustrate the absurdity of the idea of something, anything existing in a superposition of states. But it's sort of it's gone into this thing where it's like, it's become about consciousness, which is not really, I feel like, what the point of it is.
I think the same. Yeah, I think another example would be, what is that guy? The guy in the wheelchair from Oxford University.
Stephen Hawking?
Stephen Hawking, and it's like the dilation of time with gravity. It was like a topology paper in the beginning. Mm-hmm. Now, like the infinite universe theory has become marvels. Like
Oh yeah,
it's
string theory
it's just become
and like multiple realities.
Yeah, it's just if
That
you
does
if
actually
you have a look at the paper, it's actually a completely different field of science than what it has become. And I'm not going to talk about it because I don't really understand it, but I'm saying that it has slowly blown up out of proportion where we even forgot where we started, right? Like, where did this information come from? Ask a 5-year-old, like, oh, what's like a multiverse? He's like, oh, this thing in Doctor Strange.
Yeah.
And it's like, wait, hold on. We've completely missed the plot. The science is like miscommunicated. And I think it does long-term damage where it's like, it's harder to reteach people and like say, actually, well, forget everything you know from Hollywood. Forget everything you know that you've read from like, science fiction. This is the science behind it. And then there was another, I think personally, for example, when they teach in chemistry the atoms, they teach a certain model of it, right? They teach the nuclear. I think there is a word for that model.
The orbital. I think there's the orbital model.
Right, but
where
I
it's
think
electrons.
there's a special name for it.
Maybe.
Yeah. So like you
I
have
know
the nucleus.
There's the plum pudding model.
Yeah. I think
Remember that?
yeah.
That's an example of the what was disproved by the Rutherford Gold experiment. I don't know why I can only remember that one, where the gold foil experiment, where they shoot electrons through a gold foil and figure out that actually atoms are mostly empty space. But before they thought it was like positive and negative charges in like a contiguous sea or something. I don't know.
Right.
And it is funny that like they teach you that as like, here, this is why the plum pudding model was incorrect. And then like most of the time also do not mention that like also the orbital one that we're teaching you is also not correct.
Exactly, right? So they would have this nucleus and electrons orbiting around. And then if you continue doing chemistry, they will actually say, if you write orbiting, we'll take marks off you because that's not what happens.
Yeah.
And
they
it's
don't
like
have orbits, they have orbitals.
right,
which are different.
And it's like, oh, then actually they have states, and actually an electron does not orbit. It has a probability of being within this state, and it's like, well, what the hell are you doing? Like, why are you like? And the excuse is it's like, oh, well, we're teaching children models of things, like simplified versions, so they can digest it, and it's like, children are way smarter than you are. They can pick things up that you haven't imagined. So like I think there's in science communication, there's a lot of weird stuff going on that's like...
Yeah. Like, and I do think it's important to like, I think like the fundamental idea of like, we can't teach children quantum physics. Like, yes, children are smart, but like there's a lot of stuff that you need to build up to understanding how things work before you can understand. Like, yes, children are smart, but like, there's just math that you need to understand for it to mean anything. But I also think like, there are times where it's like we can be clear that like, hey, this is a simplified explanation. Some of this stuff, this will get you, this works well enough for certain contexts that you're going to be using. You could be using this for. There's more to it. We're starting with this simplified, and we will expand it. It will expand if you continue pursuing. There needs to be
a disclaimer.
Yeah, just like some understanding of like, because like we like it, and it's like we know where the edge of. We know what we don't know. We don't know, right? We know where we still have to figure stuff out. So you can tell people like, here is the end of current scientific knowledge, and where this is where the boundary is between like things we know and things that are theory. And you can just, even when you're way behind that, you can still point and say, this is where you will eventually get to. You don't need to understand anything about that practically for a practical application. But I do think I think to your point, it is important that as you are learning about those things, you know that there's more out there. You know that this isn't the end of the track. And then at a certain point, you will get to the point where it's like, beyond this is research. Beyond this is like, you need to go out and figure this out. Someone needs to go out and figure this out.
Would that not feel silly if you were just like, let's say to a 15-year-old, you're like, hey, this is an atom. This is also not the atom. We're teaching you a simplified model that, you know, will be. There's a Russian joke. I'm not sure if it was translated, but there was like, as a kid, like you go to kindergarten, it's like, oh, forget what your parents told you, and then you go to middle school and it's like, oh, forget everything you learned in kindergarten, and then you go to like on, and at university it's like, oh, forget everything, and then you go to industry, it's like, oh, forget everything you learned at university, and it's like, oh, like can I just learn something once?
Yeah.
That's like the actual thing of our like the best of our understanding. So I don't have to forget all these simplified models that will like break.
This is the XOR.
You get the team culture wrong, you failed. You get the wrong people on board, you know, you have too many different people, you fail. You have two people who are, you know, all on the same page, you fail.
Yeah, because making a robot is very vertical, I think would be the way to say it, right? Like,
What do you mean by vertical?
like you have to have a few people, like you take like the buckets of people that you need. You have to like vertically integrated business, right? Like it's like one where maybe this is wrong, but like they do each bit of their full product. They're not like an intermediary, right?
Right.
As opposed to my understanding is a horizontal structure business is like we do one thing and we do that one specific thing, and that's what everybody here does, is that one specific thing. And our job is to be that one specific thing for a lot of people who need that one specific thing. Whereas like if you're making a robot, like there's not the one thing, right? A robot, you cannot distill a robot down into one
It's a system
thing.
of a lot of things, right?
So
You can't
have
do the one
instead of
thing.
having a big group of people all doing the same thing, you have lots of little buckets of people stacked on top of each other in this vertical metaphor that I'm trying to shoehorn in here. You've got these little buckets of people stacked on top of each other, and you have to have all those little buckets of people. You can't like pull certain middle ones out. Maybe you can take out like, you can cut some off of the bottom and the top, but you can't cut anything out of the middle, because if you lose one of the intermediate steps, then you just can't have the robot, or the robot's going to end up breaking, or you're going to end up in some situation where where the people at the bottom of the pipeline, again, because you could put it on the side if you didn't want it to feel like the bottom is the bad part of it. The beginning part aren't going to be able to get their thing all the way to the end. And so you have to have like diversity in like, you know, just background, because you need people who can you need small groups of people who can do a lot of different things. Like you have these specialists, but you have like a couple specialists for this, a couple specialists for this, a couple specialists for this, a couple specialists for this. I enjoy that because I like learning about that whole vertical stack.
That's exactly what
I like following the path of like everything from like whichever way you want it. You can start it from like the code and then follow the code into the, you know, so that's you've got the math that goes into the software, that goes into the firmware, that goes into
like the electronics board, and then the board into the casing, and then the casing, you know, surrounded by more of the same, and
then like on top of that, it's like, okay, then you get like a robot, and then you've got like, okay, now how do robots interact with each other? So you're at a level higher than that, and you can, and then but then also like there's different, like it's not just a vertical stack, right? There's like different branches too, right? So you've got the hardware for controlling, like you've got the software to firmware for controlling a motor, but then you've got the hardware of the motor that then gets fed back into the software for everything, for like another thing up the chain, and so like kind of bounces in and out of itself a bit too.
You could be writing software for the highest levels, and even you'd have to consider at the end when you built the robot, you always have to consider the environment and the user, and then you can write software for them, and then those guys might have their own hardware, like a some sort of controller, and it's just. I tend to like that. Like, I think a lot of the roboticists that I speak to, they tend to be attracted to that complexity and breadth. And but I'm actually interested in the complexity. I'm interested in like what really. How do I tune these little because everything exists on the spectrum, and I'm trying to understand which spectrum is like to play with, like how does culture affect the development, like how does let's say knowledge gaps, like your knowledge and the way you acquired it, affect the whole team. I think that's really interesting to me.
Yeah.
What do you think you would specialize in if it wasn't, like, let's say you had a free reign on your career and you could choose, like, I mean, obviously sometimes you don't get to your plans, it doesn't go as you always wanted, but what about robotics really excites you that you would like continue to work on?
Man, the most like there's a certain aspect of like I like doing the things that I'm good at, because then you have an idea, you do the idea and it works and you're like, yes, satisfaction. But like I think like I want to be careful about saying systems engineering, because I feel like that's very broad.
Yeah,
and it can mean a lot of
gets
different
negative
things.
connotations a lot because it's like,
but like
overused.
Really understanding like the whole, like, I mean, that's part of like why I started in physics, was because like with physics, like I want to understand like from beginning to end, like every step. I don't want to just be like, oh, that's not my department, I don't really understand what's going on there. I just know, I know, right? You could, we were talking about how like the way you learn things informs how you understand the world. And like now and that's definitely true, especially as control, because I describe everything as like a control problem now. I don't think everything is a control problem. It's just my go-to metaphor, because I can twist those knobs and get what I want out of it. But like you can exist in an environment where you know your input, right, in the production pipeline, and you know your output, you know what you need to have for your output. So you know what you know what you need to take and what you need to spit out, and you can get really good in that little insular area, and not know anything about anything outside of that. But I like knowing all of the little bits and pieces and like following the thread of like, here's this line of code that I've written. This is how it like goes through everything and ends up on some behavior. So, but yeah, like, so, and I don't even really know a lot about systems engineering as like a field, right? So that's why I'm sort of have trepidations, because like maybe the thing I'm describing isn't exactly what would be covered by the name systems engineering. But like expanding my ability to work on different parts of the sort of the stack of making a robot, I think was sort of like my main goal right now. It's just because there's this other thing. It's like, I think it's a fairly commonly understood phenomenon where it's like at the beginning of learning a new subject, you get to learn a lot.
Yeah.
And then you get like this hype of like, oh wow, like I knew nothing about this and now I know all this. And then as you get further, you're like, now I'm just like, nothing's happening.
Yeah, you learn less and less.
You're getting less and less new knowledge per minute invested. And when you try to do like a spread out approach, right, you don't get a lot of depth. So like, you know, for me, it's like, okay, here's my little corner. You can't see this. Here's my little corner where I am getting depth, because like you need depth to like really contribute. But then I also want to get even just the surface level of a bunch of other stuff. Because I think it's useful, but also I think it's really cool to be able to understand those things and understand, like, even just at a surface level, what the implications of everything that you're doing actually is.
I think a lot of roboticists are like that. And I want to see whether it's like that thing where people who are like that go in the field, or the field demands that, so it turns people into those kind of people. Because I'm exactly like that, where I'm like, I like to know a lot of things. I don't tend to specialize. I tend to like learn, pick up more and more, and I really enjoy the full stack. But then I'm like, in robotics, that's exactly what you need to do. So I'm like, I don't really catch like, is it the people who make the field, or is it the field that makes the people?
That's an interesting question. I don't think I could really. I can tell that like this isn't something that only applies to robotics for me. So
Because I've
and it
met
was-
people, like, if I talk to like an electronics engineer and I'm like, well, how does this really work? And it's like, oh, well, I learned this layer of knowledge, right? I don't really know the physics of the transistor. I don't really understand the software behind this chip. I just understand this layer, and that's enough for me. And I was like, no, wait,
Yeah.
what do you mean you don't have to figure out the whole thing? Like, how can you live? Like, how can you go to bed not knowing everything?
Yeah, like if I worked with, I mean, and I certainly with electronics, that is probably my biggest, like, this just seems like magic to me. I don't
Right.
I don't know exactly what's going on in a circuit board, but I would like to know. And if it was something that fundamental, like, I mean, like, I learned enough about computers to, like, know what happens when I write code and it gets compiled and it gets changed into assembly at some point, and then that assembly gets turned into the bits and bytes, and then it just becomes like a series of electronic impulses, right? Like, I know it, then like that level is like, okay, I've got it. Like, obviously I don't have all the details. I don't know everything about, like, memory caching and stuff. That's stuff that I'll learn. I have, like, basic ideas, but, like, I don't know how to control it or anything. But, like, I can follow the thread. But yeah, with electronics, like you said, like, using transistors but not knowing how they worked, like, that would bother. I knew at one point how transistors worked. I did learn it, but I forgot.
This is the XOR.
Video games provide you with what smart kids need, like gifted kids, is that they are built in a specific way that always feeds you with not entertainment but challenge, right? Every level has a level above it, and gifted kids tend to love consistent challenge. Whereas at school, they do a semester, the semester is over, right? Like, you do your homework, you can't get more homework. You if it was too easy, they'll get bored. They're just like, well, I've done my thing. Let me go play video games, because video games, they are tailored to constantly challenge you and push you. Every level is just more difficult than the other, right? It keeps that tension alive. And he was basically making a point that, school system for, gifted kids should actually focus on tailoring the system to, like, always, give them the challenge, like, build them up to be something great, right? Okay, that was the rant over. And I was like, well, hell yeah, that's very true. I see that pattern in video games, that they are tailored psychological, like, manipulation tools. Like, they are designed by people to trigger specific responses, and they're like, now that we've developed into, like, this, the video game industry has developed into this, like, huge field. They're now something completely different, right? They're like a means of a storytelling. They're a means of capturing attention.
Right.
Like, they are, like, people wanna, like, they're so good, people wanna live in them.
Right.
Like, if you were to ask people to give up their current life to go live in a life of, I don't know, Elder Scrolls, they would. That's how good it is.
I wouldn't. This seems like a bad time to me
Yeah.
personally. But
You. I don't know. What's your favorite game? Like,
for me, it would
Zelda.
probably be Pokemon.
Yeah, you would go into Pokemon
I
World.
would, if I was given this is slightly tangential. If I was given the choice to stay here or go to Pokemon World, I would stay here because I have friends and family that I care about, and I would miss them deeply. And I'm not saying that to be cheesy. Like, that would be the legitimate
Right.
calculus of, like, I would be miserable.
Which game
if
would make you give up your family?
I don't think there is one. But if let's go into the idea that I have been ejected from the world that I am in now. Which one? Where am I going to end up? That would probably be it.
Pokemon.
Yeah, it's like a Solarpunk Utopia, man. Like,
Solarpunk?
yeah, it's like near futurism. Like, if like the actual, like, world building of Pokemon is like near futurism, post scarcity, like Solarpunk maybe is a little bit more modern.
I've never heard of it. I've only heard of Cyberpunk.
Solarpunk is, oh boy.
What's
it's
the
a
other
whole
one?
can of worms.
That's the most
Steampunk.
Yes.
Yeah.
Yeah.
Yeah. So it's like near futurism, very much like the principles of it. It's a very like, unlike like you have steampunk, and you have cyberpunk, and these are like cool, like worlds that are cool to see how they work, but you wouldn't want to live in them necessarily.
Yeah.
Like, oh, you might want.
Well, cyberpunk is like dystopia, basically.
Cyberpunk is dystopia. Steampunk is like, oh, look at this cool way to like, oh, it's very mechanical, but like also it's not like the only reason for liking it is it's like an escape. Is you wouldn't want the actual real
cool cosplay.
Yeah,
but
yeah.
you're like,
not,
you don't really see.
No one's trying to get to steampunk.
Right. Exactly.
Solarpunk is like is this weird intersection of like taking like, oh, like these big like, you know, green energy technology based stuff, integrating it with like harmony with nature, but it's not just fiction. Like there's another side of it that's like aspirational, because, you know, people care, like that's one of the hot topics of the modern times is like, how do we move into these different sources of energy and like different technologies and caring about the environment and all of that. So there's an interesting tension in like people who are just like, I'm just creating a cool art thing, man, and people are like, no, with this, your art needs to give an accurate idea of what would be sustainable and what would be a good thing to target for Solarpunk.
I think there was a book, and it was
We've gotten
called.
very off topic from your original.
No.
I can circle back around.
No. It's called. I think the book's called Luxury Communism, and there is a term that is basically like post excess or whatever. What's the term?
Post scarcity.
Yeah. It's like basically when we figured out all of manufacturing, basically anything is like available on demand, and we can focus.
There's not resource. Resource is no longer a driving like form of conflict.
Has everything they
has
need,
whatever resource that
and
they
can
need.
Focus on.
You don't have to worry about food scarcity. You don't have to worry about housing scarcity. Like stuff where it's like you don't have to worry about like living, because for however society has figured it out, everybody has what they need to live. And so you're not there. Then so like there's, you know, it's a very broad term. So you can be like, well, now countries don't go to war over resources because everybody has everything that they need. And it's like, and again, it's like there's an intersection of like this artistic idealism where it's like, I'm not actually like making a pitch of like how we should do things. I just like to imagine a world that is like this. And then people were like, no, I'm interested in like finding out how we can do this in different ways, not just like post scarcity. So because I like the aesthetic. Like I think the aesthetic is neat, like this harmony of science and nature. And to go back to one layer, that's like one of the reasons I like Pokemon is like that is like one of the core thesis of it is like this, like people doing stuff out in nature, but like there's no like, oh, the technology is bad, because like technology is also a fundamental part of the world building, both in nature and in the more civilized, less naturey areas. So like that's there's also a lot of like I talk about this on my podcast. I'm going to shelf for myself for a bit.
Yeah.
There's
I'm going to cut it out.
Yeah. There are things that, because it's made by a corporation, it ignores certain like sources of like stress and like real world issues that would exist in a situation like that.
Say that again.
Yeah. Like there are ways that things work in that world that rely on
In Pokemon. Right.
That rely on philosophies that are kind of detrimental to like the way the world is now, right? Like just as an example, in Pokemon, almost every single conflict is resolved by some representative of the natural world being activated by the things that the bad guys are doing. And working to stop them, and you help by aligning yourself with them. But there's this idea that if someone tries to do something bad, that there are forces out there that will naturally oppose them, and all you have to do is align yourself with those forces. Whereas when you think about like climate change, it's like, no, we can't just like wait for like, there's not like, nature isn't just going to reset itself to our benefit without us doing anything. Like we have to take an active approach. So like that's I want to be clear when I'm like saying like the utopia is one that like there's the fictional utopia, but there's like the philosophy behind that utopia, right? That you have to talk about when talking about any utopia. That I don't want to like say that, oh, I support all of the implications of what this utopia would mean. Yeah.
I understand. I think to circle this question, it was basically that video games are like on a surface level just a pastime entertainment, right? But they have innate psychology and philosophy like ingrained into them that, you know, attract certain games to certain people. And now that the games have become even better, there's more of that, right? Like it's not just a game now, it's like a worldview, right?
Right.
To give an example, like I chose my degree, which was biomedical engineering, because I played Deus Ex. That it's all about augmented cyborgs, augmented people, like advanced prostheses and like, you know, people with artificial eyes and artificial limbs.
Yeah.
And I was like, this is so tight. I'm gonna change my life and go into that field. I'm gonna study this as a degree, right? So I want to ask you, for example, like what influences, give me an example of like an influence, because I know you like video games. Like, give me an influence of like a game that was so fun, like an idea that was so life-changing. I mean, the Pokemon example was really good, but was there something that was like so inspirational, so life-changing for you that came from a video game?
I mean, like a fascination with robotics definitely came. It's a chicken and the egg sort of thing. Like I don't know if I like this because I like robotics or if I like robotics because I like this. But there's a game series, Mega Man. Anyone who knows me knows I love Mega Man. And it's all about like androids, and like the main thesis of the game is you get dropped in. You've got six or eight bosses that you can fight. Each has their own level, and you can pick which order you go to them in. And then when you beat that boss, you get their weapon, which is usually some sort of representation of an attack that they do on you in their boss fight, and you can use that weapon in the other stages. So like there's lots of different things that I like about, like I like the fact that you can go in the game in any order, so it really increases, like you can play the game over and over again and have a different experience because you can have different solutions to the same problems each time based on the tools that you have available to you, based on the order that you go in. But then also just like this like you being a Swiss Army knife hero, those I find myself really attracted to, like situation TV shows and games where like that the protagonist is like someone who has a lot of like these different tools in their tool belt, and they can solve problems in creative ways with those tools. But it's not like, oh, I've got one power. It's like, oh, you've got like these different, often like mutually exclusive, like you can only use one at a time. So like using one has an opportunity cost of using another. And like I'm sure that is informed, like, you know, because we've talked about like how many different things are involved in robotics in general. So maybe that's also influenced, like,
yeah, I can see that,
the way that I think about, like, the way that I enjoyed jumping into a different fields, because it's like adding tools to my own toolbox, and I can solve problems in creative ways based on completely different fields that I know little bits and pieces about.
This is the XOR.
There's an interview question that gets asked a lot, and I like it. And now I ask people about it in the podcast. It's like, well,
Oh boy.
let's say you have you join for a specific role, and they ask you, well, what do you think is the coolest thing in your field? And at the time, it was an interview question for Arrival, and I was like, I don't know. And they basically, at the time, there was a SpaceX launch where they like double landed, like from space. And they were like, oh, you can't use that, basically, because it's in the news. Like, you can't.
Yeah.
So I was like forced to come up with a cool thing. And I was like, oh, I don't know, man. I don't really follow my field news like that. But now I'm going to put you on the spot. Like, what do you think is the coolest recent thing that you've seen in robotics that was like, wow, this is the next thing?
Let's see. Yeah, because like I remember my answer to this question when I was asked it in interviews was the Perseverance rover, which is, I feel like maybe kind of be cheating in the same way that the SpaceX double launch is cheating, because it was like huge in the news at the time. Like and like other things where it's like, I mean, like in Control, this is also like a thing, but like the thing that I think about a lot is the James Webb Space Telescope, which the Control part of that has ended.
I don't know what that is.
It's a telescope. So you know Hubble?
Yeah.
So it's like it's been sort of marketed as the successor to Hubble. So basically, it's this big old telescope that we shot into space. It has like this foil heat shield that's like super thin and fragile, but it's necessary because it's an infrared telescope, which means that like heat would disturb the instruments. Basically, because in outer space, things are accelerating and moving away from us, and that shifts the wavelength of light because the speed of light is a constant. So in order for the physics of the speed of light being a constant to work out when things are moving, the frequency of the wave has to change. So things moving away from us move into the red and infrared. And so to take infrared pictures, it needs to not be overwhelmed by the heat of the sun. So it has to have this heat shield, but it has to be a light heat shield so we can get it up into space. And so that makes it fragile. So they had to do all of this stuff, all of this testing to get it up there. And then it gets up. Now it's up there. And once it cools down, it can like look back into the history of the universe to like, what is it? I think it's 50 million years after we think the universe started, which is, to my understanding, much further back than we've looked before.
Wow. How recent is this?
How recent
Like
is
this
like this?
launch.
Like this whole thing has been happening over the course of like this year. Like the actual experiments start like in a couple months. I don't know when we get results from those experiments, but it's like exoplanets and beginning of the universe. And there's this one really famous Hubble picture where like the story goes that they pointed it at like someone said, hey, use your time on the Hubble to just point it at a blank section of sky, like just a dark section. And all the scientists were like, oh, this is a waste of time. There's nothing there. If there was something there, we'd be able to have detected it by now. And they did it, and it was absolutely filled with galaxies and stars and stuff and it just immediately showed that the universe was way bigger than had been previously predicted. And so now they're going to do it again. And, you know, there's expectations on what we'll see, but maybe it'll be another earth-shattering revelation. But even just like, you know, looking for exoplanets, looking at planets we already know are exoplanets and seeing if they could actually like support life. Like there's a ton of cool stuff that this thing could find. And like the way that they got it up, it like the control, it's not super controls, to be honest. But like just the fact that they got it up and there were so many points of failure, so many things could go wrong. And as far as it seems so far, everything has gone perfectly. And at least it's been marketed as a complete revolution in like the next generation in like a big leap of like space observation. Looks really cool. So I've been just following it. Like when do we start getting stuff? When do we guys start getting like new things? So that's been exciting.
See you next time on the next episode of XOR.